Good evening, students. In the last class, we have discussed about the minors and cofactors. I recall your memory regarding the minors and cofactors with synopsis. Minor definition, cofactor definition, and minor of an element is denoted by M of ij. Cofactor of an element is denoted by capital A of ij, and also one important note mentioned earlier. And some examples of the minors with the second order matrix and also third order matrix along with the cofactors of the determinant. You know how to find the minor and cofactor of the elements with some examples in earlier class. Am I right here? But now we shall begin with the next topic, last but one. This is in the determinant, that is adjoint of square matrix. Adjoint of square matrix. The adjoint of square matrix can be defined. The adjoint of a square matrix is defined as A is a transpose of the matrix formed by the cofactors of an elements of the determinant of A. Let A be a matrix of 3 into 3. A11, A12, A13, A21, A22, A23, A31, A32, A33, A be a square matrix of order 3 into 3. How can you define an adjoint? The adjoint of matrix A, is the transpose of the matrix formed by the cofactors of an element. Already, you were very much familiar with the matrix chapter in SSLC. In the SSLC, you know the definition of transpose of matrix. I recall. A transpose of matrix is defined as, it can be defined as the number of rows are converted into columns or columns are converted into the rows. That is called a transpose of matrix. The adjoint of matrix A is said to be the transpose of matrix formed by the cofactors of an elements of the determinant of A, and it is denoted by, or it is written as adjoint A. See here, let A is third order matrix, A11, A12, A13, 21, 22, 23, A31, A32, A33, then adjoint A is equals to, after finding the cofactors are always denoted by capital A in the earlier minors and cofactor topic. So hence, adjoint A is equals to transpose of the matrix formed by the cofactors. Here you see capital A11, A12, A13, A21, A22, A23, A31, A32, A33. The transpose means 3 rows, 3 columns are there. Rows are converted into columns, A11, A12, A13. First row can be converted into first column. Second row can be converted into second column. Third row can be converted into third column of the square matrix of order 3 into 3. Hence, this is known to be as the adjoint of A. This is known as the adjoint of A according to definition of an adjoint. Then the result is A11, capital A11, A21, A31. Why we should write capital A instead of small a? Capital A defines here the cofactor of an element A11 formed by using the square matrix. By leaving the first row and first column. Am I right here, students? Already you recall your memory from the previous topic. Then, for the square matrix of order 2, how do you find the adjoint of A? See here, one of the example given for the square matrix of order 2. Let us see. For the square matrix of order 2, capital A equals to A11, A12, A21, A22. In this example, the adjoint A can also be obtained. The adjoint A can also be obtained by interchanging the A11 and A22 and also by changing the signs of A12 and A21. Then we get the adjoint of square matrix of order 2. How can you find the adjoint of square matrix of order 2? Is differ from the adjoint of square matrix of order 3. Only thing you keep it in your mind. Only you see capital A is one of the square matrix A11, A12, A21, A22, 2 into 2 order of matrix. In this matrix, A11 and A22 are principal diagonal elements. A21 and A12 are the secondary diagonal elements. Means the adjoint of A can be obtained by interchanging the principal diagonal elements to the secondary diagonal, interchanging the principal diagonal elements and also changing the signs in the secondary diagonal elements. So, adjoint A is equals to, I have written here. Am I right here? Will you see? Then A11, A13, A21, A22. Yes. Am I right here? A11, A12. See, adjoint A is equals to A11, A12, A21, A22. Then only thing I have marked with the box of red color. Principal diagonal elements. Interchanging the elements of principal diagonal and only thing changing their signs of the secondary diagonal element. You see in this square box. Am I right here? Then it can be represented as interchange of elements. A11, A22. A22 can be right here and A11 can be right here only. And A21, A12 change its sign. Always it is plus, but now I have changed here by minus. Again minus. Change in sign and interchange of elements. Am I right here? Okay. Then, 1 minute. Therefore, in this manner, we can find the adjoint A of square matrix of order 2. Is it clear? Is it clear? Okay. Then we come to the next, that is theorem. Next, continuing the theorem. One of the theorem is there. If A be any given square matrix of order n, A be any given square matrix of order n, then we have to prove that A into adjoint A is equals to adjoint A into A, which is equals to determinant of A into I, where I is the identity matrix of order n. Okay, once again you read it. Yes, once again, can you please? Yes. Then, how can you show that? See here, one more thing. You know very well the theorem statement. What the theorem states that if A be any given square matrix of order n, then A into adjoint A is equals to adjoint A into A, that's equals to determinant of A into I, where I is the identity matrix of order n. It can be verified by using A. Capital A is equals to A11, A12, A13, A21, A22, A23, A31, A32, A33, then adjoint A is equals to given by capital A11, A12, A13, according to the definition of adjoint. Capital A defines here cofactor of the element A11. It can be written as in the conversion of rows into columns, which is new determinant formed that defines the adjoint of A. So, capital A11, A12, A13, A21, A22, A23, A31, A32, A33, this is the adjoint of A of matrix, square matrix. Since sum of the product of elements of rows or column with corresponding cofactors equals to the determinant of A, and otherwise the value becomes 0. Here, so for that purpose, we have to prove that. We have to verify that. Then A into adjoint A, capital A into adjoint A is equals to A into adjoint A equals to determinant A 0, 0, 0, determinant A 0, then 0, 0, determinant A. That's equals to, take determinant A as a common factor, then in the square matrix of 1, 0, 0, 0, 1, 0, 0, 0, 1, we get the square matrix of order 3, especially that is called identity of matrix. That's equals to determinant of A into identity of matrix. Therefore, A into adjoint A gives the result of determinant of A into I. Similarly, we can show that adjoint into A is equals to determinant of A into I. By using this and this one, hence we have to verify that A into adjoint A, that's equals to adjoint A is equals to determinant of A into I. Yes, hence we have proved. Then, after this, we have to know about. After this, we come across to the next one is singular of matrix. Singular of matrix. What we have studied here? Already you know the definition of adjoint. How do you define the definition of adjoint? The adjoint of a square matrix A is defined as the transpose of matrix A, where A of ij is the cofactor of an element small a of ij. Hence, adjoint of the matrix A is denoted by adjoint A symbolically. And also, after the definition, you know how to find the adjoint of square matrix of order 2. After that, then we have proved one theorem. If let A be the any given square matrix of order n, then capital A into adjoint A is equals to adjoint A into capital A, that's equals to determinant of A into I, where I is the third order matrix of identity element. Then we come across to the next, that is singular of a matrix. A matrix A is said to be singular if determinant of A is equals to 0. Determinant of A equals to 0. For example, the determinant of matrix A is equals to 1, 2, 4, 8. Yes, 1, 2, 4, 8. In this determinant of matrix, multiply principal diagonal elements minus secondary diagonal elements, which gives the result 8 minus 8, which is equals to 0. Yes? For example, determinant of matrix A is equals to 1, 2, 4, 8. That's equals to product of principal diagonal elements minus secondary diagonal elements, which gives the result of 0. Hence, this is called a singular matrix. Then non-singular matrix. A matrix A is said to be non-singular if determinant of A is not equals to 0. Determinant of A is not equals to 0. Hence, for example, the determinant of matrix A is equals to 1, 2, 3, 4. Then determinant of A equals to 4 into 1, 4, minus 3 2s are 6. Hence 4 minus 6, which gives minus 2. This is not equals to 0. Hence this defines non-singular matrix. Singular matrix means by evaluating the matrix, we get 0. Then that is called singular matrix. By evaluating the square matrix of order 2 or 3, then which is not equals to 0, that is called non-singular matrix. Okay, you know singular and non-singular. We'll solve some problems based on it in solving of the problems section. Next, we continue the theorem, one more theorem. If A and B are non-singular matrices of the same order, then A into B is equals to B into A are also non-singular matrices of the same order. Yes, do you know? A and B are the two non-singular matrices of same order. Means you sometimes you take 2 into 2 order or 3 into 3 order either. Then the A into B, product of AB and product of BA are also non-singular matrices. This is the next theorem. Then another one theorem is there. The determinant of the product of matrices is equal to the product of their respective determinants. Am I right here? The determinant of product of matrices is equal to the product of their respective determinants, that is, determinant AB is equals to determinant of A into determinant of B, where A and B are square matrices of the same order. This is one of the theorem. Yes, you keep it in your mind. In the earlier theorem, A and B are the non-singular matrices of same order. Then AB and BA are also non-singular matrices of the same order. We get it. In this theorem, the determinant of the product of matrices is equal to the product of their respective determinants, can be mentioned together by, that is, determinant of AB is equals to determinant of A into determinant of B, where A and B are square matrices of the same order. Then the next one theorem is there. What it states: if A is a square matrix, A is invertible if and only if A is non-singular matrix. The statement of theorem can be expressed if A is a square matrix of capital A. Means if A is a square matrix and A is invertible if and only if A is non-singular matrix. How do you find